Good morning. All right. So sorry about the past two classes. Well, you had a test too, so I feel like I haven't seen you guys in forever. Happy to be back. So hopefully you were able to watch the videos that I've had from when I taught it on exponents and logs, the rest of it. So we're going to start trig today. And we're going to do kind of a mix of chapter 5 and 6 because they introduce the same concepts but two different ways. So we've just kind of cherry picked what we want to show you guys, and you can read the sections if you want to know more. But everything I'm giving to you is all you'll need to do some trig. So we are starting trigonometry today. Oops, that doesn't have an R in it. Metry today. Okay. So chapter 5 and 6. Chapter 5 and 6-ish, right? A little bit of bouncing between the two. Okay, so we'll start in chapter 5. We'll call it chapter 5, and then we'll talk about the unit circle, and then we'll introduce some trig functions. SOHCAHTOA might ring a bell, so that's going to come back into play, right? So trigonometry are things like angles and sine, cosine, tangent, and their graphs. We're going to talk briefly about those two. So let's get started here. So like I said, if you haven't watched those videos for the rest of chapter 4, then do that on your own time. It was weird because my section is a 2-hour block, and you guys have the hour and 20 and 50 minutes, so it's a different. But the videos, if you start where I told you to start, it's exactly 2 classes worth of material, so worked out pretty well for you guys. Okie dokie. Section 5.1, we're going to talk about just briefly about the unit circle. We need to know about just some basic things about the unit circle. So it is a circle, so we know the equation for a circle. In fact, if I draw an XY plane here, oops. Let's see if I can draw. I always forget that it'll do that. And I don't use it like I should to make a perfect circle. Okay, so here, the radius on the unit circle is 1. It's centered at the origin at 0, 0. So that means that this arm, right, at each of these points, we know where these points are, right? And so we know that this point must be at 1, 0. This point must be at 0, 1, right? So we can move around the unit circle, -1, 0, and 0, -1, right? So already we know 4 points on this unit circle, and that's going to serve us really well. So, uh-oh, not good. We're all losing our voices. The unit circle, let's just establish here, is the circle of radius 1, is the circle of radius 1 centered at the origin in the XY plane. Right, so that's what we drew here. The equation is, well, for any circle, right, x squared plus y squared equals r squared. But in our case, right, we established that the unit circle has a radius of 1. So x squared plus y squared must be 1 squared, right? So here we have any circle, the unit circle. And so what we can say, well, 1 squared is just 1. So usually we just use this last one, right? So we can do things like show that points are on the unit circle. So let's do a quick example just using x squared plus y squared equals 1. Okay, so show that the point 1 root 2 and 1 root 2, oops. So 1 over root 2, 1 over root 2 is on the unit circle. So here, right, x is 1 over root 2 and y is 1 over root 2. So what we can do, if it's on the unit circle, then x squared plus y squared must be 1, right? So I'm going to start there and say, okay, x squared plus y squared, I'm going to ask, does it equal 1? And I'm not sure yet, but if it does, then it's on the unit circle. So we have 1 over root 2 squared plus 1 over root 2 squared. Still don't know if it equals 1. So because I'm dividing in here and I'm taking the square root, I can use those exponent laws that we established way back in chapter 1, right? And I can bring this exponent inside. And so I have 1 squared over root 2 squared plus 1 squared. Okay, what happened? Jumped up. 1 squared over root 2 squared. I'm going to make sure it equals 1. So I have a square, which essentially cancels the square root, right? So, and then 1 squared is just 1. So I've got 1/2 plus 1/2. Hey, that sounds like 1 to me, right? But let's just write it out. 1/2 plus 1/2. It does equal 1. Therefore, the point 1 root 2 is on the unit circle. Woohoo. Okay. So if we kind of had to map it out here, oh, hi, Beezers. 1 root 2, 1 over root 2, 1 over root 2 is going to be here at the halfway point. I know that because I know that. But what we'll find is that we'll kind of move around the circle and there will be some key points, some key stopping points on the unit circle that we need to know where they are. And 1 over root 2 is one of those. We already know 4 of these stopping points, right? Just knowing that it's a unit circle, so the radius is 1. So whenever it's kind of parallel or perpendicular to the x-axis, then we know the point, right? 1, 0, 0, 1, depending on where you are on the circle. So let's talk about terminal points. So we can move around the unit circle, okay? Starting on the positive x-axis is usually where we start, and that's going to be kind of a default starting position. So we can move around. We can move around the unit circle, starting at the positive x-axis. Starting at the positive So the reason I couldn't have you guys on Monday was because our dog had to get her teeth done, but they had to pull 2 canines, which keep her tongue in. So we'll see if her tongue starts slipping out. She's still really cute though. She won't let me pick her up. She's still mad. Okay, so what we're gonna do, right, is we're gonna start on the positive x-axis. So what that means is that we'll have some sort of, well, we'll have a unit circle here. We'll pretend that's a nice circle. So we'll start here. Okay. What we're going to be doing is we're going to move around this circle. And as you might imagine, right, if we move kind of around the circle, we're going to be talking about moving some angle, right? You might, if you've done trig before, right, you might remember the struggle with radian and degree mode on your calculator, right? So we're going to head down that path again. But hopefully we'll kind of be able to keep track of which is radians and which is degrees. If you have to be in degree mode, there will be a little degree indicator on the angle. Okay, so we'll start talking about angles first. So we move according to an angle. We move according to an angle, okay, in radians. Okay. So if we let t and then t or theta, whichever you prefer, often angles are denoted by theta, which is the Greek letter theta. Okay. And it looks like this, right? So maybe I'll write a little blurb before I put that in. Let's write a note here. Note: angles are often denoted by theta, which is spelled like that, Theta. Okay. So usually if you see a theta, it's denoting an angle. Just to keep it simple, we can start by calling the angles t. So let t be the angle. I'm not sure if you saw, but I just this morning, so I don't expect you to have seen it. But I posted a handout for today. So a handout, let's see here, like this, okay? And it's just to save us quite a bit of writing. And it's also a nice reference page for later. So we'll kind of draw from this. So later on, I'll pull in some of these images. So, but I posted this on Moodle. So, I mean, you can kind of number them and reference them in your notes or whatever, or check them out in my notes when I post them after class. But just so you know that they're there, and we will be going to them a little bit. So if we let t be the angle, then a positive angle, right? Typically we move clockwise, but a positive angle is going to be moving this way, so counterclockwise. Whereas a negative angle is just telling you, hey, move clockwise, right, down from the positive x-axis. So as long as you keep those in mind, right, you can move clockwise or you can move counterclockwise. Most often we open up this way, which is probably what you would do if you had to draw You know some trigonometry already, presumably, right? You can draw a 180-degree angle. You'd probably go, whoop, right? Halfway through the circle like this, whoop. That's 180 degrees. So we know some of these already. And you would likely move in the counterclockwise direction. So then if t is greater than 0, so positive, we move counterclockwise. And if t is less than 0, we move clockwise. Okay. What's kind of neat about and unique to radians is that on the unit circle, the angle is actually also the distance on the arc. Okay, so note, again, so many notes here, but note that the distance traversed, actually, maybe I'll remove this note. It's more official than that. The distance traversed, I'm just gonna start over. Scratch that, just the fact. Here, maybe we'll say that, fact. Usually I have what I call little fun facts. They're just facts, but little fun facts, I call them LFFs. So a little fun fact is that the distance traversed along the arc of the unit circle, is the same as the angle t, okay, in radians. This is because, and I'll just mention it because Shaun has it in his notes, so in case you need to refer to it, but as long as you remember that the weird part about radians, and the reason we use them also, is because that distance that you've traveled is also the angle. So that's kind of weird, but really useful. All right, so this is because S is r theta, right? So where theta is the angle, like I said, r is 1 on the unit circle. And S is the length of the arc, or the arc length. So because the radius is 1 on the unit circle, well, then the arc length is equal to the angle. Okay, so what this looks like, if you have a unit circle here, then let's say this distance, okay, this distance is t. Then if we draw here, let's use green, then what happens is that this angle is also going to be t. This is the angle and this is the distance, but they're going to be the same. T, the angle, is equal to t, the distance, in radians. So when we think about these, well, I think it's easier to think about, you're kind of walking around the unit circle, you walk, and you can walk in a circle. But really what we're talking about is the angle and where we end up on the unit circle after going this angle amount. Okay? So even though it doesn't, it looks weird to have t equal to t, but t, the angle, is equal to t, the distance, because the radius is 1. Okay. Okay. So what happens if I tell you, okay, you're gonna go move some angle, right? So you start on the positive x-axis, and then just like here, right, you've gone a distance of t, you've ended up at some point, and that's what we call the terminal point, right? Terminal is the end, right? Terminus, and so it's where you end up. Okay. The point pxy is where we end up. She's a pet girl. She can't be tamed. The point pxy is where we end up after moving some angle. Oops. After moving some angle, okay, and it's called the terminal point. And it is called the terminal point. Okay. Okay, so again, I'll draw another unit circle here. They're all the same. Oh. So here, if I've gone some angle, let's stay in the first quadrant for now, right? If I've gone some angle t, then I've ended up at this terminal point pxy. Okay. Let me see, I'm not going to skip ahead too much, but I will point out here that what we'll find later is that the x is actually the cos of t, so the cosine of t, and the y is actually the sine of t. So that's where those trig functions come from, right? You might remember SOHCAHTOA, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, right? We'll refresh those. But that's going to be an important kind of feature of the unit circle, and just kind of looking at the terminal point. Well, if I know where I ended up on the circle, I also know the cosine of t and the sine of t. Like I said, I'll bring those up later, but I just wanted to introduce those. So what we have is a whole distance around the unit circle is going to be 2 pi. Okay, so 1 lap around the unit circle is just a circumference. The circumference of the unit circle is c equals 2 pi r, right, in general, but again, we use the fact that, well, here r is 1, right? So 1 lap around is going to be 2 pi times 1, which is 2 pi. So 1 lap, I think we all kind of know what I mean by that. So 1 kind of cycle, or kind of 1 lap around the unit circle is 2 pi, right? A distance of 2 pi, but also an angle of 2 pi. That's what I'll say here, is a distance / angle of 2 pi. Okay, that's important, right? We also know that, okay, well, we can establish some things using that. Okay, so here, if I'm talking about this angle here is going to be 2 pi. If I asked you what a full rotation was in degrees, right, you would probably tell me 360. So that's true. Right? 360 degrees. So what that means is that 2 pi is 360 degrees. What if I wanted to talk about just half the circle? Well, if a full rotation, notice that we're starting here on the positive x-axis and then my angle is going to here. So a full rotation is 2 pi. Well, if I'm doing half of that, 2 pi over 2 is just pi, right? So in radians, it's pi. But you also know that if I did a complete 180, right? It's even an expression, then you've gone half the circle, right? Or 360 divided by 2 if you prefer. 180 degrees. So in radians, pi, or 180 degrees is pi radians. We actually don't usually put any units on radians. Here I'm doing it to emphasize, but really 180 degrees and then is equal to pi. And then it assumes that the pi is radians because we understand that we're talking about an angle here. Okay. So notice here, I want to just notice the degree symbol. Okay. I want to just highlight that it's always, so if it's in degrees, there will always be a degree symbol. Whereas in radians, we don't necessarily have a unit and we don't need to have a unit. Right here, if I say 2 pi, I know it's going to be radians. Whereas I have to say 360 degrees, otherwise it's assumed 360 radians, which would be just around the circle a ton of times, right? So the degree symbol is going to tell you whether you need to be in radian mode or degree mode. And I know that sounds obvious, but it's actually really hard when you're first starting, right? And so, but just keep an eye out for that degree symbol. Okay. Hmm. 360 degrees, 2 pi. And here I'll just say radians. Often we don't write any units for radians. So 360 degrees is equal to 2 pi, and then it's understood that it's radians because it's an angle. So what we want to do is we're going to look at some common kind of cutoff points, and we'll start with the basics, right? We've already talked about some cutoff points, but just knowing that a full rotation is 2 pi, a half a rotation is pi, right? A quarter rotation would be pi over 2, right? Pi over 2, 2 pi over 2 is just pi, 3 pi over 2, and then 2 pi, right? So, or 4 pi over 2 if you prefer. So, example, if we have to find find the terminal point of each real number. So A is going to be t equals pi over 2. And B, we're going to have t equals negative pi. Remember, negative just tells you the direction that you're going, right? Here, this negative tells you that you're moving clockwise. That's all it's doing, but the angle is still pi, right? Pi radians. Okay, so we can put these on some unit circles. Here, I'll draw one for each of these. Okay. So we know, okay, if I go a full rotation here, that's 2 pi. We also know that a half a rotation is pi. So pi divided by 2 must be this quarter way mark, right? So here, what we've got is we can say, okay, well, from here to here is pi over 2. Okay. If we wanted to, right, this full rotation here, or half rotation, would be 2 pi over 2, which is just pi, right? We could go kind of all the way to the next stopping point, right? That would be 3 pi over 2, and then all the way around would be 4 pi over 2, which is just 2 pi, right? So we know that pi over 2 is this first kind of quarter cutoff point. And we also know, because we're on the unit circle centered at the origin, right? I know that this point, pxy, is going to be when x is 0 and y is 1, right? Just looking at where you are on the xy plane. Okay. So find the terminal point. Well, the terminal point here is 0, 1. Okay. So therefore, terminal point of t equals pi over 2 is 0, 1. Okay. Now we can do the same thing, right? Just keeping track of these pretty basic quarter way marks, right? Pi over 2, pi, 3 pi over 2, 2 pi. So now if I have pi, I know I'm going half a distance, but I have to go clockwise, right? Because it's negative. So we get, from here, I'm going negative pi, which puts me on this arm here. And because I'm on the unit circle, again, I know where this point is, right? I've got a radius of 1, so I've moved out, but in the negative x direction. So pxy is going to be negative 1, 0. Okay. Just knowing where x is positive or negative, where y is positive and where y is negative, right? That's going to be really useful. So therefore, the terminal point of t equals negative pi is negative 0, or sorry, negative 1, 0. I'll read them backwards. Looking at each of these, right? Well, what if we just kept going and going, right? So what if I went pi over 2, so I went to here, pi over 2, and then I went another rotation. That would be pi over 2 plus 2 pi, right? So what's going to happen is because we have this kind of circle property, right? It's cyclical, and so now every 2 pi, I'm going to end up at the same point. Okay. We see that if we moved 2 pi, which is the distance of the circle, distance of the full circle, we would end up at the same terminal point as each of these points, right? It doesn't matter if you started at pi over 2. So if you started here and you moved 2 pi, well, then you're back here at 0, 1. Or if you started here and you moved 2 pi, well, you can move 2 pi this way or 2 pi this way. It doesn't matter. You end up at the same terminal point. So we see that if we move 2 pi, which is the distance of the full circle, we end up at the same terminal point. So, as a kind of follow-up example, are there any other angles which have the same terminal points as, let's say, t equals negative pi? So, are there any other angles which have the same terminal point as t equals negative pi? Question mark. So the terminal point here is negative 1, 0. Okay. So it doesn't actually matter if I move clockwise or counterclockwise. As long as I move a distance of 2 pi, I'll end up again at negative 1, 0. So what we can say is we can move t equals negative pi or pi. Notice that it doesn't actually matter if you move negative pi or pi, right? You end up at the same point. So that's another point or another angle that would put you in the same terminal point. In fact, I'll put that down here. T equals pi has the same terminal point. As t equals negative pi, right? Puts us in the same place on the circle. As well as an angle of pi, let's just use the positive version because it's a little bit easier to deal with. Pi plus some multiple of 2 pi. And we're allowing for any multiple of 2 pi as long as we're moving a full 2 pi, right? I can move 14 2 pi's, 14 trips around the circle, but I would still end up at the same terminal point. So how we write that is pi plus 2k pi for k in the set of integers. So remember the set of integers, I didn't do that very nicely, right? It's kind of a fancy Z here with kind of a bold back. This is the set of counting numbers, right? 0, 1, 2, 3, 4, 5, 6, blah, 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 all the way to infinity, right? But we're doing whole numbers. So k is essentially the number of rotations. The number of rotations, which has to be a whole number. And then 2 pi is just the distance of one rotation, right? So if I'm saying 3 is the k, so 2 pi 3 times is 6 pi, right? So then if I move 6 pi, I've done 3 rotations, but I still end up at the same terminal point as if I move just pi. So if we consider something like, actually, let's just make it another example. Find the terminal point. Find the terminal point of t equals 8 pi. Okay. 8 pi, okay, well, you can map it out if you want. All right, here we go. So I've gone 1 rotation is 2 pi. It looks like I can move another rotation, which is gonna be 4 pi. Another rotation, I still have room for another rotation. 6 pi, oops, here. So that's 6 pi, and then 8 pi, well, that seems to just put me back. So this is 8 pi, but it's gonna have the same terminal point as the starting point. So here, this is at, because even though I draw my angles inside each other, we're still just moving around the unit circle. I'm just trying to show how many times I've moved around the circle, right? So this point is at 1, 0. Therefore, the terminal point is at 1, 0. What if we kind of went the other way, right? So what angles have a terminal point of 0, 1, right? X is 0, Y is 1, so now I'm up on the positive Y axis. So let's say, for example, what angles have a terminal point of 0, 1? Okay. So I can map it out again. Right. I know here is 0, 1. Okay. And I also know from before, right, we established some of those key cutoff points. I know that this angle is pi over 2. But I also know that if I go pi over 2 and then plus 2 pi in either direction, I end up at the same point. So what we can say is that t must be, so the angle t is pi over 2, pi over 2 plus, and we use that same notation that we used earlier, 2k pi, 2k pi, where k is in the set of integers again, right? Counting numbers. So as long as I'm moving a multiple of 2 pi all the way around, then I'm going to end up at the same terminal point. Okay. Oops. Okay. Let's see here. An interesting property, okay, is going to be, like I said earlier, but now we're going to establish it, is that the x value on, so the terminal point has an x and a y value, right? And that terminal point, the x value is actually the cosine of the angle that you moved, and sine is, or the y is actually the sine of the angle you moved. Okay. So a useful property is that the xy points of the terminal point, oops, of an angle on a unit circle, of an angle t, let's say, t or theta, doesn't matter, they're interchangeable. So useful property is that the xy points on the terminal point of an angle, so weird, we had to move some angle to get to a terminal point, okay? Is that the xy points on the terminal point of an angle t on the unit circle are equivalent to, so we say that we can use pxy. This p is just indicating that it's some point with values xy or coordinates xy is going to be cos of t sine of t. Okay, so what this says is that the x value is the cosine of the angle, whereas the y value of the terminal point is the sine. The y value is the sine of the angle. Weird. Yeah. Recall from kind of math before, SOHCAHTOA, right, says that sine of t is the opposite over hypotenuse. Oops. And the cosine, cos of t, so cos of some angle t is the adjacent over the hypotenuse. We're going to focus on just sine and cosine for now because they're the values that we get from our terminal point, right? So knowing the terminal point could be useful for finding sine and cosine, but we're going to focus on just the so and the ka for now, so sine and cosine, and then we'll get into the other trig functions as well later. And just for kind of your memory, right? Opposite, hypotenuse, adjacent, we need to know which ones are which. And so here, if you have some angle t, so if this is the angle t that we're talking about, then when we say opposite over hypotenuse, well, the opposite is the length of this side here, which is opposite of t. And the hypotenuse is always going to be the side that's opposite the right angle. So the 90-degree angle is this little square here. So this is the hypotenuse. And let's see here. Hypotenuse. This is the adjacent. And this is the opposite. Let's see if I can. All right. So it just depends on where your angle is. If it's up here, then of course this is the opposite and this is the adjacent, but this will always be the hypotenuse in this case. So if we know the lengths of these sides of this triangle, then we can find the sine and the cosine. Kind of weird to make this connection. All of a sudden we're talking about triangles when we've been working on do you want me to share this password? I guess. Weird. He needs the Wi-Fi. Thought he had it. He should. Anyways, so okay, but we're going to be able to make the connection here between some angle, the angle on the unit circle, and some key triangles. We're going to have two special triangles in particular that we're going to talk about, and they're going to help us find terminal points. Okay, so that's the connection here. Just bear with me. So let's see here. Example, find the sine of pi without using your calculator, and then we'll confirm it using your calculator. First, without your calculator. Then confirm using your calculator. So here my angle is pi, right? And the sine is actually referring to the y value. So here, right, the sine of t, the angle, is the y value of the terminal point. So if I know the terminal point, then I know the sine value, right? So we can draw our unit circle. We're going to do a lot of these, okay? And I know that if I move pi, so here, pi is my t, right? T equals pi. So if I move a distance of pi, I end up here. So kind of halfway, okay? But I also know that here, pxy, you don't have to write the pxy. In fact, just to simplify things, how about we just write -1, 0, right? That's my terminal point, -1, so x is -1, and my y is 0. So what we just established here, up here, is that, okay, well then the cosine of pi must be -1, and the sine of pi must be 0. Okay. So here, oh, maybe let's do this. Cos of pi must be -1. And the sine of pi must be 0, right? So we can use it. We use the terminal point. We use the terminal point to find that sine of pi is 0. Okay. Now, radian and degree mode on your calculator, it depends on what calculator you have. I have this this kind of fun one, but I don't know kind of what calculator you have, because you're allowed to use whatever you want. But what you need to make sure, and what I'll do is I'll show you on the Desmos calculator, which is the free app. You'll need to make sure, so there's this that app. It's good, not great, but it's a free calculator, so who can complain, right? Notice, so here I don't have a pointer, but up here, I'm changing between radian and degree mode, right? So if the degree mode is showing, I want to turn that off. I want radian mode. So we need to make sure, because pi is in radians, right? There are no degrees units, so I have to be in radians. So if I go to my functions and I take the sine, and then notice that there's a pi button here, sine of pi, well, the sine of pi turns out it's 0, right? So, and that's exactly what we found. Okay? So, we need to make sure our calculator is in radian mode, since pi is in radians, right? It doesn't have that degree symbol. Doesn't have the degree symbol. In degrees, right, if I change it to degree mode, notice that the sine of pi changes to 0.0548. So you don't want that, right? You want to be in radians. Okay. Okay. What if we had to find, so now, right here, I kind of walked you through it, sine of pi, okay, and then confirm it using your calculator. Now we're just going to do it by hand, and we'll check with our calculator briefly, but find the cosine of negative pi over 2, over 2. Okay. Well, we should be a little bit more comfortable. Oops, hey. My iPad keeps gapping out. It's not good. If I'm moving a negative direction, I'm moving clockwise, and pi over 2 actually just puts me here, right? It's a quarter way mark. We know that because we know those quarter way marks pretty well by now, right? And so here, negative pi over 2 puts me on this arm. And because I'm on the unit circle, I know that terminal point is at 0, negative 1. Okay. Okay. Weird. There's a typo here that luckily I didn't pay attention to. But now I'm like, did I do it wrong? No, I did it right. There's a mistake. So here, right, knowing that the cosine is the x value and the sine of the angle is the y value, well, now I know that the cosine of negative pi over 2 must be 0. So the cosine of negative pi over 2 is 0, right? And just for, to make things easier, right, what's the sine of negative pi over 2, just so we have it under control? And sine of negative pi over 2, well, we already have it, it's negative 1, right? It's the y value. So here, so the cosine and the sine. Huh? So kind of the first Not, maybe not the first on the handout. I think I put, yeah, I just put a little reminder of essentially SOHCAHTOA and a little bit more. We'll refer to this a little bit later, probably next day when we talk about the other trig functions, right? So the 4 other trig functions that we'll work with. But for now, we're just focusing on sine and cosine. But this is the table that I wanted us to bring in because it introduces these 2 special triangles. And we can use these special triangles and to find terminal points of a lot of different angles. Okay. So I'm going to bring it in, copy, and I'll paste it, but I'll write a little intro here. Okay. We will use special triangles to find terminal points on the unit circle. To find terminal points on the unit circle. Okay. So first things first, right? We've talked about the quarter-way marks, right? Those quarter-way marks are some obvious cutoff points, and we established that, okay, well, 180 degrees we know is the same as pi radians. 2 pi radians is 360 degrees, and so we just established a few more cutoffs, right? 0 degrees. We've looked at 90 degrees. So now we just kind of chop it into thirds and in half. And what happens is we get from 0 to pi over 2, but then we've got these key check-in points, pi over 6, pi over 4, and pi over 3. So what's going to happen is pi over 6, pi over 4, pi over 3, and then pi over 2. And we'll be able to use these cutoff points to solve pretty well any angle. Okay, so these are the key ones to know. And so definitely have, you know, the special triangles and maybe even these conversions just kind of memorized. You don't need to memorize anything because presumably you'll have access to everything during the test. So, but just have it available somewhere. Okay, like I said, we're going to focus on sine and cosine today, and then we'll move on to the tan and the cosecant, the secant and the cotangent. But for now, just focus on sine and cosine. Okay. So, pi over 6, pi over 4, and pi over 3 introduce 3 new terminal points, right? Or 3 new angles / terminal points that will be useful. Right? Just like we use the terminal point, knowing the terminal point of negative pi over 2, well, it's supposed to be a 2, to find the sine and cosine, we can do the same thing, but we'll do a little bit more work because we need these special triangles. Okay, so I'm going to try to put all these on the same unit circle. Wish me luck. Okay, because what I'm going to do is notice that 30 degrees is pi over 6, right? So here we could replace the 30 degrees with pi over 6. 45 degrees is pi over 4 for both of these, and this is pi over 3. Right? So we can work in either degrees or radians. Actually prefer radians for now because we're not as comfortable with radians. So this is how we get comfortable. So here we go. I'm going to draw a huge circle, but we're only going to focus on the first quadrant, okay? And you'll see why in a little bit. Okie dokie, here we go. Actually, let me just draw the first quadrant here. Okay, so here, okay, and then I'm just going to indicate that this keeps going here. It is the unit circle, okay, but I've zoomed in on the first quadrant. Zoom in on the first quadrant. Okay, so what happens is we've got 3 points, right? So we started here and we went here. So we know those points, 1, 0, 0, 1, okay? Okay. You know what? Maybe I should use some boring colors for those because we've already established those. And I want to use the colors for something else for these new guys. Okay, so if I go halfway here, and I'm just going to try to do my best at eyeballing it, okay, then what happens is halfway, somewhere like that, okay, here, if the full distance is 90 degrees, then this distance must be half of that, 45 degrees, which is actually going to be pi over 4. Right? Okay, so pi over 4, if we just look at our special triangle, okay, here's my 90-degree angle. What I'm going to do is I'm just going to shove this 45 degrees, or you could do this one. Notice that it's the same, right? So we can flip it whichever way. But the 45-degree angle has to go and match the 45 degrees. So what I'm going to do is I'm going to have something that drops down like that. Okay, so here, there's my right angle. So of course I have 45 degrees or pi over 4, which we'll get in the habit of using pi over 4 instead as the halfway mark here. Okay, but this is a distance of 1, 1, and root 2. And this is just from 1 squared plus 1 squared is c squared, which is root 2. Okay. A squared plus b squared equals c squared. Okay, so the sine of pi over 4, right? Or let's start with the cosine, which is the x value. xy is the cos of pi over 4 and the sine of pi over 4. Okay. The cosine of pi over 4 is the adjacent over hypotenuse, okay? 1 over root 2. So this is going to be 1 over root 2. And then the sine of pi over 4, opposite over hypotenuse, 1 over root 2 again. Okay. Clean this up, should look like
I'm here.
Root 2. Okay. So if we know this, this special triangle, right, then we're able to find the sine and cosine very easily, right? What if we kind of let's take, let's take the 30-degree angle, which is pi over 6. So now, if this is pi over 2, then what I can do is I can kind of make third of the way marks. Right? And this is going to be a different angle. This is going to be 30 degrees, which is pi over 6. And if we have a look here, I went too far, didn't I? Partial. Got to erase this a little bit here. You'll see why in a second here. Because I have to drop down for a distance of 1. Okay. Hey, no, it's the 30-degree angle. That's for the 60-degree angle. Nope. Undo, undo. There. We're fine. Sorry about that, guys. Because if we're, okay, so what I have to do is I have to take this angle and I have to shove it in. So I kind of have to flip it and shove it in like we did with the 45-degree angle. Okay, so what that translates to is that this is a distance of, root 3. And opposite is 1. So that's where my 1 is. And then the hypotenuse is 2. Okay. Same idea though, right? If I need this XY point, just jumping to the cosine of pi over 6, well, the cosine of pi over 6 is going to be the x value. So the cosine of pi over 6 is the adjacent root 3 over the hypotenuse, which is 2. Root 3 over 2, and the sine is the opposite over the hypotenuse, which is 1/2. Okay. Now I use the same triangle, but the different side, so the 60-degree or the pi over 3 angle, and I shove that into the corner, and now it has to drop down. So now, can I use this mark here? Actually, it might be easier if I draw it there. Oops. Didn't want to straighten out, okay. This is not going to look good. It's supposed to extend. Why am I saying that? Well, because this length is 1, right? And so when I drop it down, right, it has to drop down onto here. So technically it should be going kind of off the page up here. Whee! But I did a bad job. It's because I got too ambitious and I tried to keep them all on the same graph. Fake triangle. Because it went off the page. Just imagine, it's a triangle, it's a real triangle. But I did a bad job. So then this angle here is 60 degrees, which is pi over 3. Okay. Well, okay, so now I've got this corner butted in, right? So this length is still 1. This, the opposite of root 3, or pi over 3 is root 3. So here I've got root 3, a distance of 1 here, and 2 is the hypotenuse again. So what happens at this point? Well, now I'm not even going to write that. Well, I should write the xy. But the cosine of pi over 3 is the adjacent over the hypotenuse, 1 over 2. And the sine of pi over 3 is the opposite over the hypotenuse, root 3 over 2. Okay. Knowing these 3 points, and you can use the special triangles, they'll be really useful. But I mean, if you don't like memorizing these special triangles and kind of butting them into your unit circle, you can just remember these cutoff points, right? What happens as you move through the unit circle? Well, here, if I go a same kind of a mirror distance on the other side of pi over 3, well, then my x just becomes negative, but my y stays the same. So what's going to happen as you move through the unit circle, right? So as you move away from the first quadrant, your x and y is going to change values depending on what quadrant you're in, right? But remembering that the cosine is your x and the sine of your angle is the y, well, then wherever x is positive, cosine is positive. Wherever x is negative, cosine is negative, and so on and so forth. Okay, so we use the special triangles to find terminal points. Or if you prefer, the values of sine and cosine, or the values of sine t or cos t. Okay. All right. There's just one more thing. I know I'm kind of running low on time, but I just want to introduce how we're going to use these terminal points to solve problems. So specifically, if we are given an angle, doesn't matter how many times you've gone around the circle. What you need is you kind of need to take away those full revolutions and only focus on the terminal point, right? And so what we do is we add or subtract, depending on kind of the angle that you're given, multiples of 2 pi until you have an angle, until you get an angle between negative 2 pi, so that's going clockwise, negative 2 pi. So here, this is the end angle, and 2 pi. So somewhere in that 1 cycle range. And since we are adding multiples of 2 pi, we will end up at the same terminal point. At the same terminal point. Okay. So here I'll say end angle, right? Kind of whatever the boil down angle is. So then you're going to draw TE, which is that kind of boiled down angle on the XY plane. then if you need to, if it's not one of those obvious terminal points, right, draw the special triangle, draw the appropriate special triangle. If needed. And then label the signs, or label the sides, I should say, of the special triangle with the proper sign. Oops, now I'm really out of time. Just a sec. Let me just finish writing this here. With the proper sign based on the quadrant and then find the terminal point. So we'll keep going with that on Friday. Sorry to keep you. But maybe what I'll do is for next day, I'll fill in these notes with the opposite. So if we have to find an angle, so I'll add on to these notes and then we can refer to them and have them kind of written out next day, because I know it's already Wednesday, so Friday classes are so short, blink and you miss them. So I'll have them pre-written out. All right, I'll let you go. Have a great day. See you on Friday.
See you Friday.